Hi, good afternoon, everybody. My name is Svandi Arkuhi, and I'm Simulation Product Manager at Intercad. Welcome to today's webinar about Introduction to SolidWorks Flow Simulation. If you could please type in that you can hear my voice and clearly you can see my desktop in a poll, then we will start our session. Okay, so we can see, everybody can see my desktop. All right, good. So let's start our work. This is the third session of design validation webinars conducted by Intercad. We are aiming to assist designer and engineer to utilize their simulation tool in their daily activities. The upcoming event, as shown, are on 13th of September, we have Design, Study, and Optimization in SolidWorks FEA. And also we have the next one on 20th of September, which is about steady state transient thermal study in SolidWorks. If you are interested on the topics and you haven't registered, please send me an email at the end of the session and I will provide the registration link for you. We are also organizing series of seminars to present the capability of the software in various applications, and this is a very good opportunity to have a face-to-face meeting with our valuable prospect and customer to understand their specific simulation needs. The first seminar is conducted by us on 26th of September in Melbourne, where the registration link will be sent to everybody in a few weeks. Again, if you are interested on this too, then please send us an email and we provide you the registration link. All right, now let's start with the topics we're covering today. First, we're starting with the definition of fluid mechanic and the branches of the fluid mechanic we have. Then we go through the basic of the fluid mechanics, where we're introducing fluid definition, normal and shear stress in fluid, viscosity, static and dynamic pressure, and common terminology we have on fluid dynamics. We also introduce the computational fluid dynamics. What does it mean? How does it work? And then we apply what we learn here through a case study, which is a manifold assembly. Within this case, we will understand and learn how we create leads, how we create a project, a flow simulation project, how we set up, how we are putting the initial conditions, and then we are also going through the post-processing options available. And if we got the time at the end, we will go through the capabilities of Flow Simulation 2013 as well. All right. Now let's start with the fluid mechanic definition. Basically, fluid mechanic is the study of the behavior of the fluid. If we deal with the action of the force of the fluid at rest, this is called fluid static. If we concern with the action of the forces exerted by or on the fluid in motion, this branch is called fluid dynamic. So two major categories: fluid at rest, fluid at motion. So we call them fluid static and fluid dynamic. And why we are trying to understand and study these fluid mechanics? Because basically all of us are floating in a let's say fluid when we're living on Earth, and this fluid is air. So we basically be taking air in and out every second. Or the blood flow in our artery or veins are simply a fluid mechanics study, or the water we drink, or the motion of the air. So any of these study which will help us to understand the action and reaction between the fluid region and the other region would be our main concern. So if you look at the mechanic, which is the physical science which deals with stationary or moving boundaries under influence of force, we end up with three main categories as solid, plastics, and fluid, where we introduce that fluid at the rest is called static, and fluid in motion is called dynamic. We simply can categorize it again on two major categories as a compressible or incompressible fluids, where if we simply focusing on the liquids, not the gas, we're talking this branch as hydrodynamic. Where in hydrodynamic category, if you are interested on the interaction between the fluids in pipes or open channel, this branch is called hydraulic. If we're interested on gas, it would be gas dynamic, or the interaction between the flow and solid bodies, this is called aerodynamics. So that is a very general overview about the different branches we can have in fluid dynamic, in a fluid study. Now, before we actually defining the fluid, let's define what is stress and what is shear in a fluid region. Imagine we have a surface with a cross-sectional area of A and a small element, dA, where a force F is applying to that. If we simply have two components of normal and tangential force, as normal force per area is simply defined as pressure, and the tangential force per area is defined shear stress. With that definition, now we can go and have a look through the fluid definition. So basically, fluid is a substance in a gaseous or liquid form where it cannot resist the shear. Look at the figure first. If we have a solid like a rubber type between the plates and we apply the force, solid can resist an applied shear by deforming, and then we have stress, strain proportional to each other. But fluid is not resisting. It deforms continuously under applied shear, as you can see, 0 to maximum. Then in some category of the fluid, stress and strain are proportional. So the main difference between the solid and fluid is the resistance to the force we apply, and specifically shear force we apply. However, there would be an internal resistance to the motion, which this property is called viscosity. Viscosity is the property that represents the internal resistance of the fluid to a motion. Because of this, the force a flowing fluid exerts on a body in a flow direction is called drag force. And the magnitude of this force is simply dependent on the viscosity. For instance, as you can see in the picture, if an object is moving through the air, we have less drag force compared to an object which is trying to move in a water. That is also can be explained here, where viscosity is defined as a rate or the ratio between shear stress and rate of deformation, where high viscous fluids such as oil, you have a very high slope, and low viscous fluid such as air, they have very low slope. Viscosity could be defined as a dynamic viscosity, which simply is a shear rate per rate of deformation, or could be a kinematic viscosity, which is dynamic viscosity per density. And also, if you would like to finding the shear force acting on a Newtonian flow, simply shear force is shear stress times cross-sectional area, which is mu, which is viscosity, a cross-sectional area, du over dy, which is the rate of deformation. All right. Next topic is about the pressure. This is the common terminology we're always hearing. The actual pressure at a given point is called absolute pressure. But considering the fact that all of us living on Earth and there is an atmosphere above us, therefore there would be an atmospheric pressure applying to everything. So this is included on any measuring device which is calibrated to 0 at atmospheric pressure. Therefore, we coming to the point of definition of gauge pressure, where absolute pressure minus atmospheric pressure is called gauge pressure. So as a summary, absolute pressure is total pressure applying including atmospheric. Atmospheric pressure is what we have from above us, and the gauge pressure is what we read in a device which is being calibrated in atmospheric region. The important fact, if we are studying fluid at rest, is the dependency of the pressure with the depth. If you look at this figure, you can see there is a big container with different shape at different section. Simply, the pressure, the static pressure at any point depends on the density of the fluid, gravitational acceleration, and the depth. Therefore, we can simply say point A, B, C, D, E, F, and G, as they are all at the same level, with the same material, then they have the same pressure, regardless of the container shape. The level or the distance from the reference surface is the same. Now, but if we move to point I, as we go more on depth, therefore that delta Z, or the distance from the surface, is increasing, therefore we are expecting the pressure rise. But the question is point I and H have the equal pressure? The answer is no, because as you can see on that section, we have mercury with more density compared to water. So although they are on the same level, as the value of rho or density is increased, therefore the pressure at point H is more than point I. But very important addition, this is what we're talking about, the fluid static, fluid which is not moving. Now, if we go to the next category, or the fluid flow terminology, we have a second definition which called dynamic pressure. And this dynamic pressure is defined as 0.5 times density times velocity square. Also, we can define dynamic pressure as a difference between total and static pressure. So, static pressure is rho density GH, and dynamic pressure is defining as 0.5 density velocity square. So, when we're talking about pressure, we have to be clear enough about what is that pressure. Is it a total, static, or dynamic? All right. Now, let's go through some classification and some common terminology we have in fluid mechanics. One of them is no-slip boundary condition, where everybody know that the flow cannot, the fluid cannot flow through the solid surfaces, and the normal component of flow velocity will be zero at the surface. So simply that the flow is sticking to the solid surface at their contact point. And because we have the viscosity, means internal resistance of the fluid to the motion, it will, this viscosity will affect the adjustant layer of the fluid near to that surface. So the resistance through the motion, it is 100% when it's stick, and then it's getting less and less until this viscosity's effect is simply ignoring. So that region, as you can see in this new figure, is here, and we call this boundary layer, where the viscous effect are important. And when we going out of this, we're reaching to the nominal velocity, as you can see here. So a study of the boundary layer is very important for us, because we get various change, very rapid change of the velocity in that area, and that could affect the flow characteristic or even heat transfer characteristic if we are interested on these phenomena. So about the classification of the flow. We can classify flow as a tool in making simplification assumption to governing partial equations. And the major equation we solve when we would like to solve a fluid domain is first conservation of mass, which is simply saying if you have a fluid region or a region which you like to study, whatever mass is coming in should go out. And the second one is Newton's second law, we're simply saying the summation of force you putting on that region will end up with the rate is equal to rate of change in momentum. So these two equations are the main equation, which they call the Navier-Stokes equation, and we're trying to solve them to analyze our fluid. In this regard, let's classify the flow. The flow regions. First is viscous and inviscid regions, like what we introduced. In the region that viscosity is effect coming to the consideration, this is a viscous flow, or let's say boundary layer. For the region where we have no frictional force acting, we call them inviscid flow region. Next category is internal and external flow. The flow of a bounded fluid over a surface such as a pipe is internal flow. We have a dominant viscous effect in those kind of flow regions. And in contrast, if we have an external flow, then the flow of an unbounded fluid over a surface such as a plate is external flow. So for external flows, viscous effects are limited to the boundary layer and wake. Next classification is compressible versus incompressible flow. A flow is classified as incompressible if density remains nearly constant. So depends on the pressure you apply. If the density is not changing, it is incompressible flow. Liquids are typically incompressible, but in contrast, we have gaseous flow, which mostly they are compressible, specifically when we have high speed of motion. A very good indicator is a Mach number to understand if the gas flow is compressible or not compressible, where the Mach number is simply defining as the ratio of actual velocity to the velocity of sound. If this value is less than 0.3, then we have incompressible flow. Less than 1 is subsonic. Equal to 1 is sonic. More than 1 is supersonic. And if it's way bigger than 1, then we have hypersonic flow. The next classification is steady versus unsteady flow. Steady flow simply implies no change at a point with the time. We have, for instance, an inflow of 1 meter per second. Now, 10 seconds later, 20 seconds later, 10 minutes later, and it's no change. On the other hand, or opposite side, we have unsteady flow, where the, let's say, transient behavior of input, or let's say periodic or oscillating, let's say, behavior or boundary conditions are simply applying to our study. Therefore, the time, let's say, parameter will divide the steady and unsteady classification for us. And the last classification of the fluid is talking about laminar versus turbulent flow. Laminar flow, as you can see on the first picture here, is highly ordered fluid motion with the smooth streamlines. You can see all the streamlines are parallel and the flow is moving very smoothly. However, the turbulent flow, as you can see in this picture, is highly disordered fluid motion and could be characterized by velocity fluctuations, vortices, and eddies. However, we have a transitional fluid where we have both effects at the same time. This is the transitional fluid, as you can see in the middle picture. One of the very good indicator of finding if the fluid is laminar or turbulent is the Reynolds number, and it's defined simply as density times velocity times length over the kinematic viscosity. This is the key parameter where we can find the flow is laminar or turbulent. Usually, for example, in a tube shape, if the Reynolds number is less than 4,000, then it is laminar flow, or both mix of transitional and laminar. And more than this, definitely we go to the turbulent flow. There are so many other parameters that can modify these indicators, such as the shape and the properties of the fluid as well. All right, now we understood the definition of the fluid, classification of the fluid, and we know what is the governing equation we have to solve. One way of approaching to the solution is the numerical process. So that's why we have created a new category as computational fluid dynamic, which is the science of predicting fluid flow, heat transfer, mass transfer, and chemical reaction, and related phenomena by solving the mathematical equations which govern these processes using a numerical process. So numerically, we're solving our fluid domain, the governing equation, considering any boundary conditions we have, and this result could be used as conceptual studies of a new design, detailed product development, troubleshooting, and redesigning. The main advantage of using CFD is reduces the total effort required in laboratory. So set up a fluid mechanics laboratory could be quite time consuming and very expensive, but having a CFD approach would just require a very powerful computer and a very good knowledge, and then we can solve the equation with so many probing tools where we can exert any boundary condition and also extract any result we would like. Let's say how CFD is working. These are sort of analysis begins with the mathematical modeling of a physical problem. For example, if you have an exhaust or a domain for bottle filling problem, this is how you define it. First, you need the geometry and you bring it to your CFD studies. What you have to know that you are going to solve the conservation of mass, momentum, and energy equation and satisfy them through that whole region. We will assign the fluid properties such as density, viscosity, specific heat, and etc. We will apply some assumptions to make it more simple, such as if the fluid is steady state, compressible, incompressible, one-dimensional, two-dimensional, and etc. Then also we will apply initial boundary condition to the problem. For instance, what is the inflow, what is the outflow, any other pressure we have, and any other conditions we would like to consider. Since we have fully defined the mathematical model based on the physical problem, then we have to do the next stage, which is the process which we call discretization. That simply means we will approximate the whole geometry and we will solve the equation on that approximation elements. So a series of cells and elements we will put to represent the geometry, and we solve this equation through all these elements. Since we have solved them, then we are able to do the post-processing process. Then we can extract quantities of interest such as lift, drag, torque, heat transfer, and etc. from the domain. Flow simulation in SolidWorks uses the same concept. It is using computational fluid dynamic techniques for solving different problem. We have various of application, and we can consider different, let's say, scenarios such as 2D or 3D analysis, external, internal flow, steady state, transient, compressible, incompressible, subsonic, and the other type of the, let's say, fluid study. And what we will do today, we will going to experience all what we define and what we understood through a case study, which is a manifold assembly. In this regards, we introduce the flow simulation interface for you, menus, toolbars, and icons. We will experience about how we creating leads and how we set up the solution, how we set up a project, and also we will go through the post-processing of the results. The case study is simply a manifold with a single entry and 6 exits. What we're trying to do to set up a project and see the fluid characteristic that could be used later on for any optimization if you would like to. But before I open the case and the study file, we mentioned something about lead here. What is lead and why is required? If you like to perform an internal flow study, all opening within a model must be covered using SolidWorks feature called lead. Simply, we closing all the opening and exit, and we create the negative volume of the solid what we have. This is, and we telling the software this is the region that the fluid exists. The surface of the lead are used to apply boundary condition, where we can have various of conditions such as mass flow rate, volume flow rate, total pressure, and fan condition, and etc. So basically, if obviously if we don't have any internal flow analysis, for example, we have external flow analysis, there is no need to creating a lead. One very important thing when you're creating a lead is to avoid any line or point contact. If this is your solid geometry and you're trying to close that area, this is what we have to avoid: line contact or a point contact. In SolidWorks Flow Simulation, we have a very good tool to examine and check if the geometry is working correct. Alright, with that quick introduction, let's go and open up the case study. Alright, so let me bring the case study here into the screen, and here it is. You can see the manifold assembly where we have a single entry and we have 6 exits. As we said, the first step is how we create a lead. If you activate your Flow Simulation tab, then going to that tab, you can see, sorry guys, excuse me, you can see there is a create lead option here where it closes opening with the solid leads. How it's work? Simply click on this. Going to the face, it will ask you to select the planar faces the opening belongs to. Then you simply click on this and you can see the lead is created. It is showing us that is being closed by a lead that been extruded through inflow region. The thickness is here. It's saying 3.94 millimeter, and we can always adjust it to be here at, for example, 1 millimeter. But again, very important, that should be always through the domain, and we have to avoid the reverse direction and make sure there is no line contact there to create the lead. So we simply can click OK, and the lead is now created. That seems to be tricky. Okay, now you can see the opening is being closed. It's through the domain, not out of it. and you have new feature added here, new part added here. Now let's look at the other side, which is the exit of this domain. You can see we have 6 outlets where we have to close them. If we click on option of lead, as this is an empty space on the exit, we have to select the surface like this, and that is showing us the whole surface is going to select it and create a lead that include this outlet and these 2 let's say bolt hole, which this is not what we desire to do. So what we do in this case, if we don't have appropriate surface on our model, one very good approach is to create a manual lead for ourselves, simply by going to assembly and insert a new component. Then the component is on this face. We are on the sketch tool, selecting the edge, select the tangency to make sure all the edges are selected, and then convert this to entity. And now we are able to ask for bus extrude, this one. So this is the scenario I'm always repeating we have to avoid. This is the lead, but we have a line contact where the flow region is behind this. So that is absolutely wrong if we do that. Therefore, we have to change the direction. One very good approach would be a mid-plan, and the thickness would be something that has not that much effect on our fluid domain. So 2 millimeter would be enough. So we created a manual lead by converting the edge on a new part, bus extrude, and then click OK. Now we have our first lead created here. So if we are interested to do the rest of the leads created here as well, then simply what we can do, go to rebuild this model and then ask for a linear patterning. So linear patterning of that component, where the direction on the edge would be this edge. On the reverse, I have measured the distance before, 120, and we need 6 of them. You can get the preview and you see it's all been created here. So clicking OK, we have our second feature as the local pattern, and now we can say we have closed all the opening and exits of the model. Now, when you finish such this operation in a fluid study, internal study, you have to check and make sure you have put everything in an appropriate way and it's all closed. Back to the Flow Simulation tab, you can see there is a check geometry tool for you, and if you click on this, it will list all the components you have in your actual model. Then you can check and see if the volume of the fluid has been created for you. If you have any edge contact or something you have forgot, then this would be 0, and there is no way that you can start the fluid study or creating a project. So before we commencing to the study, we have to understand this, and we check and we can show the volume of the fluid. So you can see the internal region of that solid base or manifold is being converted through a volume of the fluid. There is a question here, is does it matter how thick the lead is? Actually, if the thickness would be matter if it's going to affect your inlet region, we have to minimize it as much as possible. Usually we thinking about less than 1% of the entry surface area, and then we will proceed with that. The rest is I will show you in the next few steps that we will get the internal, let's say, face of the lead to apply boundary condition, and our flow region is starting from there. That would be a compromise of what you are actually having. If you have more thick, let's say, lead, you will sacrifice a bit of your flow region from that point. If it's less, then you will have appropriate flow region here. Okay, now we have closed up our model, and here it's ready to create a flow study. Now, what we do in this case, SolidWorks Flow Simulation will provide us a very good tool for the project creation, where through a wizard you can specify all the general setting of your flow simulation. So by clicking on this, you will be asked to first enter the project name, which we call it manifold. If you have different configuration on your actual model, you can simply choose that, and then you click next. Next item you have to specify is the unit system you would like to choose. From SI units to the other units are available, and also within that unit you can go and, for example, change the length from meter to millimeter, for instance. So whatever you would like to put here, all this could be changed about the units, and also decimal place, the decimals in the result display, and etc. So we accept this and click next. Next is the analysis type, where it is internal or external. You can choose from any of these. If you are interested on heat transfer, you can check the value of heat condition in solids. You would like to have radiation, time dependent on transient analysis, gravity included, or rotation included. There would be reference axis. You can always change it to X, Y, Z, depends on your actual geometry. And then click next. Is what is the default fluid or working fluid in your domain. You have a list of gases, liquids, non-Newtonian liquids, compressible liquids, real gases, and steam, where in our case we are interested on air. When you double click, it will come to your selection. You can add or remove later on, and also it will show you that the flow characteristic considered as laminar and turbulent. You can include high Mach number flow or humidity as well. By ticking that, you will ask to enter a few things, let's say, in advance. Next is about default wall thermal condition. We assume that we have adiabatic walls. There is no heat transfer through the walls. You can simply go and change this if you have heat flux on your wall, heat transfer rate, or wall temperature. And also you can specify the wall roughness in any data if you like. We accept whatever we have here. And next is about the initial conditions, where it's asking about the domain thermodynamic parameters such as pressure and temperature, which we consider as atmospheric pressure and 20 degrees of Celsius. The domain is at 0 velocity in all direction, and turbulence parameters are simply considered as what we have here. Clicking on next is coming to the result and geometry resolution selection. So result resolution is minimum 3, it could be minimum 1. The recommended initial is 3, and if you increase it to other values, you have finer mesh or coarser mesh, but you can have, it would take longer or shorter time to solve the domain. So accuracy could be affected considerably, and also computational time will be affected as well. So you can have a manual meshing or refine your meshing or applying local meshing to increase your, let's say, accuracy. and optimize your study time. But here we simply finish, and now you can see we have a new tab added here where we have a simulation tab, and this is called manifold. So we simply understood how we creating a simulation case. First thing you can see here is a computational domain created around this model. We're simply showing us where is the actual model located. If there is subdomains, we can see it clearly here. Now here we can apply our boundary condition. If you have porous media, we can apply it here, goals, initial mesh, and etc. Alright, the first thing we have to do this is to insert the boundary condition where we specify an inflow and we specify an outflow. So right click on boundary condition, insert boundary condition, then we come to this point, a new communication window where we would like to apply inflow here on the lead. Now it is very important, as I've introduced the lead before for you, is this lead is starting from that surface and ended 1 millimeter down here. It is more than important to apply your boundary condition on this face, internal face. How we do that? We simply clicking on the face, not selecting, clicking, select other. It will show us the other faces could be selected. Usually the first option, and you can see I have selected that green face which is inside the lead. Simply means the fluid study is starting, or the initial condition is starting from that point. So that is the first important thing. Then the first type of the flow is fluid opening. Next is pressure openings. Third is the wall. In a flow opening, we have inlet mass, inlet volume flow, inlet velocity, inlet Mach number, or it could be assigned as an outlet, outlet mass flow, outlet volume flow, velocity, and Mach number. Where in this case, we would like to insert a volume flow rate of 0.05 meter cube per second. Be very careful about the units. We can assume it as a normal to face, could be swirl, or could be 3D vector. About its distribution, now it is uniform, or if you like, you can assign any table or a formula definition to the distribution of your inflow. We accept it as a uniform, and then thermodynamics parameters. It's showing us atmospheric pressure and 20 degrees. Also for turbulent parameters, we have 2% with that length as the turbulence intensity and length. You can switch to K epsilon model as well. For the boundary layer, it's turbulent boundary layer, and the option is creating associated goals layer. I'm going to introduce this later on. So we accept this boundary condition and click on OK. So you can see we have created an inflow starting the internal face of the lead through the whole domain. Alright, now we have to assign the same thing to the outflow regions. So zoom in and then again insert boundary condition, and then we go to opening to the pressure type. We would like to assign static pressure here on the faces of. Again, select other, inside face of all we have here. All these faces are coming to be same static pressure applied on them. Clicking OK, and then we have the static pressure applied on the outlet. Alright, now there is no other boundary condition we are thinking to apply here. Now we have to introduce the goals. SolidWorks Simulation contains built-in criteria to stop the solution process. However, it is best to use our own criterion by using the SolidWorks Flow Simulation called goals. We can specify any goal by right-clicking and the variety of options we have. Global goal, goals at points, surface, or volumes. Let's introduce a surface goal now. For instance, if we choose right-click surface goal, then any surface we would like to, let's say, control is going to be first selected. For instance, in that lead inside area surface, we would like to control the volume flow rate. Clicking on this and simply clicking OK, then we have volume flow rate to be controlled over that face. We can have similar thing for our outlets. Surface goal, and we simply selecting that face, this face, all the faces on the outlet, all together, and then simply we can have all these surfaces as one goal or create a goal for each surface and then simply come and say volume flow rate is what I would like to control. You can see 2, 3, 4, 5, 6, 7, 8 is being created for that 6 surfaces. Now the next thing is equation goal. We can simply ask to control the addition of these flow rates all together to be controlled as well. Make sure there is no missing points and everything is under control. To the outlet and create an equation goal here. So these goals are simply being assigned to have a specific control through our domain, and then simply our model is pretty ready to be solved. All right, let me bring our, just to save the time, let me bring the solve model for you and simply open up this. 1 minute, guys, sorry. All right. All right, so we have created the study here complete, and let's bring this on to you if it's helping me. All right, so we have this one, and let's put our command manager somewhere in the right place. All right, so as you can see, this is the study we have created. We applied inflow boundary condition, static pressure on the outlets, and we inserted the goals as you can see here and some of the outlets. All right, now we are ready to run the project. Run is here. When you click on this, it will ask you for a new calculation or continue calculation, okay? And then you click on run, it says run at this computer, and it uses 8 CPUs, and click run. Then you will have a new communication window coming forward. Now, first is the information. So the status is on calculation. Everything is being prepared, the flow cell and partial cell. You can assign any goals table where goal plot, it is showing us how the convergence criteria is getting met. Here it is. For instance, for inlet volume flow rate, the current value is that one. We haven't achieved any convergency not yet, and this is the graph on the convergency. That is all available for other goals you have assigned. The next type of the control is where you put and insert a preview. By doing that, you will make a preview of your actual results over the domain which is getting solved, currently under the solution. You can see the velocity magnitude is changing and it's processing. The status bar is showing you that 52 iteration is done and where you are on your calculation stage. You can always make a pause, stop, resume at any time, or make more preview. Insert a preview. This is a top one. For instance, I would like to have a right preview where I'm clicking OK, and this is a right preview at some location. It's showing me how it's getting progress and so forth. So at as many as you like, you can insert and trace these convergency and the actual situation in the solution process. Now you can see in the goals we have inserted, then we have achieved some, let's say, convergency, still is checking, solution is finished, and this is what we achieved on our, let's say, resolution. If what you have achieved is not what is you like to have, you have to go and refine your, let's say, refine your accuracy of the result, like one we showed on the beginning. So when it's finished, then we can close, and now we can see we have result, one file being assigned, and this is the result section for us. I can see a question here. It says there are 8 flow rates, 7 openings. I believe that would be that done a mistake from me. So we are 8 goals when we have 7 surfaces. So it could be, as look at the goals. Here it is. 1 is for the inlet, 1 is for each outlet, and 1 is being assigned as total of this. So you can create as many as goals you would like to achieve, because the solver is able to control individual as well as any equation. So we assign 1 individual to all of the surfaces, as you can see, and also we concern that the total mass going out of those outlet surfaces are important for us. We would like to make the iteration in a way that is achieving some specific criteria. Alright, so that doesn't really matter. If you have 8 surfaces, you're creating more than 8. That doesn't really matter, and you can simply put as many as you like. Alright, now let's explore the result option. The first result option we can get is a cut plot. Simply insert a cut plot, then it's showing you, could be from front plan, or you can change it to a top plan, right plan, or anything you like. How it's getting displayed is a contour plot, is it isolines, vector plot, or it could be combination of all of these. What property you would like to see, for instance velocity, and also you can crop the region in a way that you like. So if I show you my first one, it is here. So I have created the top plan with the contours, and it's showing me the velocity. Now zoom in, you have this distribution. This is one of the cut plans I have introduced. We have the legend here. We can always modify the legend. It's showing us the velocity. It could be changed to anything else. The high range and lower limit and higher limit is basically here. We can change this to make it more specified. For example, we are interested to see the region within 2 meter to 5 meter per second. And if I say OK, then this is how does it look like. That is, then you can play with the upper limit and lower limit and get it back to its original shape or its reset value and click OK. You can also insert as many as you like and also show different, let's say, values here. For instance, another contour pressure, contour plot with the pressure and click OK. Then we have the pressure contour. Simply I have to hide this. And this is the pressure distribution. Again, you can have a modification to let's say upper limit and lower limit if you like. By right click here, you can animate this. It will going through the result. You can see how it is changing and how the flow is developing from inlet to outlet over the time. That's true. We have static analysis. We had a steady state analysis, but again, when we're solving a float region from 0 to its nominal value, which is the final value, which is valid point for us, the solution is getting divided by the time steps, and this is showing us from 0 to your nominal value, how does it getting developed and progressed. Okay. So I'm stopping this and show you the next option we have. The next option we have would be could be a vector plot. We can modify any of our let's say contour plot to a set of vectors. So I have to close this, come to edit definition, and instead of instead of contours, I'm selecting vectors and clicking OK. So this is the vector pressure applying on this sort of let's say result presentation. Okay. Also, we can have a surface plot option. So let me hide this, and this is surface plot. So we would like to see the pressure. Let me show this. We would like to see the pressure on the whole domain, and simply if we go to edit definition, we will apply a contour, and then we will specify pressure, and this is the surface which we said use all faces, or you can go and click on any face you like. Then click OK. You can see the pressure distribution in 3D format. You can always make a prop. So the prop tool is here. Go at any place, put your prop tool, and simply look at the pressure value at any specific region if you like. The other good option we have is the flow trajectories. If I'm hiding this, is your flow trajectory region. Simply it's asking you how it's a pattern, it's a pick from the screen or XYZ location from which face. So this is the face. How many of them we need, what is their appearance, what is their distance, where it's start, where it's stop. So if I go to edit definition here, we simply created a pattern from a face, which is that face, with the number of the points 16, showing as a pipe. The distance between those is 0.001 meter, and it's showing us the pressure. If I click OK, the flow trajectories are shown here. From outlet to inlet, that's been created. You can have a multiple choice of different faces all over the place. The other option we have in flow, let's say post-processing, is to create an XY plot. So insert, and based on any line or a sketch you have, you can simply select and then say which parameter I would like to see. For example, pressure and velocity. Then you ask for show. This is the pressure and velocity change over the time and over the lengths. This could be exported to Microsoft Excel, and if you click on export, then what you have is the graph in a first tab automatically for velocity, that is for pressure, and this is the data being plotted. That's all happening automatically. So you can make a tailor-made report in any way you like to create. All right, so we simply concluding by saying set up a flow simulation in SolidWorks could be easily done within a wizard, and simply we have to understand the boundary condition, the common terminology, and trying to translate correctly the physical properties of our problem to a mathematical model. Be very careful about creating leads, and then you have a lot of options to make a tailor-made or let's say results presentation for yourself, including the cut plots, flow trajectories, surface plots, contour plots, probing, and also 2D let's say data extractions. Let's go to the last slide what I have here, where it is talking about the capability of CFD in multi-domain. We are let's say we are able to cover different let's say areas such as non-Newtonian fluid, compressible liquids, laminar and turbulent and transitional fluids, swirling flows and fans, perforated plates, porous media, cavitation, and also droplets. And also we can perform the solid particle studies. In a CFD region, again, we can consider wall thickness and roughness. We can have multiple rotating frames, water vapor condensation, slip condition could be also inserted. The relative humidity could be considered in any, let's say, study, and also we can get gravitational effects be considered on any CFD. For the heat transfer area, we can have conjugated heat transfer studies in fluids and solids. We can have surface-to-surface radiation. We can simulate contact resistance, heat sink simulation, thermostat, and thermoelectric cooler, let's say, model. All right. So that concludes to our, let's say, presentation today, and let me see if there is any question here. We're running out of the time, sorry guys, but I hope that is helping you. Let me see if there is other question being arised. All right, questions. All right. Assigning goals. Okay. We got the question is what is the purpose of assigning goals? Again, it's to create some specific convergence rate and convergence control. We would like to have these surfaces, as you know, the numerical approach is to have an iteration method of guessing and converging. So if we would like to have a very accurate answer, then this is the place. Let's say we're putting goals and we're specifying how accurate our result should be there. The other is, has been any verification of SolidWorks result with any other industry accepted methods? That is a common. So SolidWorks simulation package is simply a standard package which all other packages are using the same numerical approach. Always it's up to the customer and the user to do the correct setting and have a reference to check. It's a numerical, but it would be, for example, if you do a prototyping and you do a 5 prototyping for your test to make sure there is no uncertainty in your laboratory, then you can reduce it to 1 and compare to your, let's say, SolidWorks or any other CFD result. And then when the results are overlapping for any design development or any modification, since your model is calibrated, now you can do the verification on a virtual machine rather than rebuild a new rig and new rig and new rig. There would be always in a numerical method of checking the accuracy, a very good translation of the results. However, there would be an overlapping, and make sure one thing is in advance. When you set up a rig in a laboratory, there are so many uncertainties and errors from your measuring tool, how you set up the rings, and everything is there, where you have no certainty that what I get from the laboratory is correct. That is the same thing when you're doing a virtual thing, a virtual study. Then we have to do the correct way of, let's say, communication and translation. So our uncertainties are happening both in experiment and numerical approach. We have to be aware and reduce them, and sometimes we have the case comparison. But the good thing about when you're doing, let's say, a virtual testing or a CFD is you can verify different concepts before within even if you're spending more time or more effort and costing a lot of money. So that is the main advantage you get. All right, thank you everybody for attending the seminar. We're expecting everybody, if they're interested, on the next week topic as well. Verse 13 of September we have design, study and optimization in SolidWorks FEA, and also on 20 of September we have a steady state transient thermal study in SolidWorks. Please register through the link if you are interested, and also we hope to see you in a seminar on 26th for more let's say questioning and more let's say practical example we have in SolidWorks. So this is my email address if you would like to let's say write it down. This video will be updated on ICD 3D channel through our website in YouTube, and the content would be available for any review. Again, thanks everybody for attending.